So for this question, what are we told? We're told particles P and Q of masses 4 kilograms and 6 kilograms. So P is 4, so acting down on P is 4G, acting down on Q is 6G due to gravity. Attach the ends of a light inextensible string. So the fact it's inextensible means the tension is the same throughout. The string passes over a smooth fixed pulley. Because it's smooth, that means there's no friction. The system is in equilibrium, with P hanging 1.75 meters above the plane. Fine, Q is resting on the plane. Because Q is resting on the plane, there is also a normal reaction force acting upwards on it, just like this. Fine. What other forces can we label in that diagram? Well, we've also got tension in the string. So we'll have tension in the string acting away from P. We'll have tension in the string acting away from Q. We'll also have tension acting away from the pulley and tension acting away from the pulley. Right, so part A is find the magnitude of the normal reaction force acting on Q. A really, really common wrong answer, so this is the most common wrong answer, would be to write down 6G. It isn't going to be 6G because although it's in equilibrium, there's also tension in the string. However, at this point, because P is not moving, it makes sense that the tension is in this string is going to be 4G. Because on P, there's only 4G acting down. The tension acting upwards must be 4G, or it wouldn't be in equilibrium. The tension is the same throughout. So if you consider just Q now, so this is just Q, so this is my particle Q. Acting downwards on Q, we've got 6G. Acting upwards on Q, we've got the tension, which is 4G. And then we've also got the reaction force acting upwards. Because it's got 4G acting upwards and the forces must be balanced, it makes sense that the normal reaction force must be 2G, because then 2G and 4G would act to kind of cancel out that 6G, keeping Q in equilibrium. Right, after that, part B, just need to read really carefully what's going on here. The mass of P is doubled. So if the mass of P is doubled, P is now going to be 8G. So let me just erase, I'll probably draw a new diagram here. Let me just erase that for a second. We've got 8G now acting down. And the system is released from rest. You may assume that in the subsequent motion, Q does not reach the pulley. But because P is now heavier, when the system is released from rest, P is going to accelerate downwards like this. Q is going to accelerate upwards like this. Determine the magnitude of the force exerted on the pulley by the string before P strikes the plane, i.e. before P gets to the ground. So to do that, we're going to resolve forces on P and on Q separately. And to do that, we're going to use Newton's law, that F equals ma. So resolving for P, so resolve for P. So on P, your kind of overall force is going downwards, that will be 8G minus T, equals the mass of P, which is 8, times the acceleration, which is A. We'll do the same thing now, resolve for Q. And in terms of Q, so Q will be moving upwards, so it will be the tension minus 6G equals 6A. You no longer have to worry about the normal reaction force, because once Q is off that plane, i.e. once it's moved up off that surface, there is no normal reaction force. So what we want to do now is we want to solve these equations simultaneously. The easiest way to solve these simultaneously is to add them together. So when it comes to adding them together, well, 8G plus minus 6G is 2G. Tension plus minus tension is 0. And then 8A plus 6A is 14A. So this is useful because this gives us our acceleration. 2G, just remember, means 2 lots of 9.8. So we get 19.6 equals 14A. And therefore A is, let's just check this, 19.6 divided by 14, 1.4. Just before I continue, I will just point out that several people were not substituting in 9.8 as your value for gravity. Really important that you do that. G in A-level maths needs to be taken as 9.8 unless it says otherwise. Now we've got that the acceleration is 1.4. we should have enough information to find the tension. So if we substitute our value of A back into one of our equations of motion up here, so we can get T minus 6G equals 6 lots of 1.4. Remember that this just means T minus 6 times 9.8. So T minus 58.8 equals 8.4. We can solve this then. T is going to be 8.4 plus 58.8. T is 67.2 newtons. If you got to that answer, it would have probably been 4 marks. This is not currently the correct answer to the question. The reason that it isn't is because we're looking for the magnitude of the force exerted on the pulley. Focusing on the pulley's got 2 forces acting on it by the string. It's got 2 lots of tension. So it's going to be 2 lots of the tension, because it's got tension acting on it both ways. So 2 lots of 67.2 is 134.4 newtons, like that. Okay, part C of this question. Determine the total Determine the total distance travelled by Q between the instant when the system is released and the instant when Q first momentarily comes to rest. So with this kind of problem, we need to think of it being in 2 stages. So I'm going to write out SUVAT twice, and then we'll talk about what those 2 stages are. Right. So the reason that we're going to use SUVAT twice is because, first of all, what's going to happen is the system is going to move. It's going to move, P is going to go down, Q is going to go up. And at this point, there is tension in the string. Okay, there is tension in the string. And so the object will be accelerating because there is tension in the string, and the force will all be there because of the tension in the string. After that, P is going to hit the ground, but Q is still going to keep traveling kind of by itself because of acceleration due to gravity. There will be no tension in the string, but there will be acceleration because of gravity. And therefore, we've got 2 parts of you've got to use SUVAT twice for these 2 different bits. So let's have a go and see how we get on. So, first bit, when there's tension in the string, the displacement is going to be what P travels before it hits the ground. So that would be 1.75. Our starting U is going to be 0, and we know it's going to be 0 because the system is released from rest. We don't know what V is. We do know the acceleration because we worked it out earlier on. The acceleration is 1.4. We don't know the time taken, but we could work it out. The thing we really need to find, though, is the velocity, the end velocity just here. And the reason we want to find the end velocity just here is because the end velocity of like the first part of the journey will be the start velocity for the second part of the journey. So that's what we're going to find now. And to find that, I will use V squared equals U squared plus 2AS. So when I do that, I get V squared equals U squared is 0, and then 2 times 1.75 times 1.4. You get V squared equals 4.9, and therefore V equals, I'm going to keep this as a decimal, as a surd because it's slightly easier, and you get V is 7 root 10 over 10. Now this is good because this is now our new starting velocity, so 7 root 10 over 10. What else do we know? We know that Q is going to come momentarily to rest. So when something comes to rest, its end velocity would be 0. We also know that the acceleration, now the acceleration due to gravity is going to be minus 9.8, like that. And this then gives us enough information to work out S, to work out the distance travelled. So again, we can use our SUVAT equation of V squared equals U squared plus 2AS. In this case, we get 0 squared equals, now V squared, just remember, we worked out here that V squared was 4.9, so in this case U squared is just going to be 4.9 minus 19.6 S. We can then solve that to get, let me just write this out slightly better, we get 19.6 S equals 4.9, and therefore we get S equals 0.25. which is nice. And then there's just one last thing for us to do. We're looking for the total distance travelled by Q. So in the first part of the journey, Q travelled 1.75 metres. The second part of the journey's Q travelled 0.25 metres. So if we do 1.75 plus 0.25, we get an answer of 2 metres, like that. Finally, for part D of this question, it's just 1 mark. When they actually do this, when this motion is observed in practice, it is found that the total distance travelled by Q is less than the answer calculated in part C. State one fact that could account for this difference. The easiest one to mention would be air resistance, because our model didn't take into account air resistance, and air resistance is likely to mean it travels slightly less distance than we calculated.